Hey guys, welcome to the 2021 F equals MA competition workthrough. So first we're going to take a look at question 1, which is to find the speed over time graph. So first thing we need to notice is that the energy is conserved all the way. So when you go from point A to point B or point C, you can see the velocity or the speed is always constant, so it is straight line. And when it goes up from here to that point, and when you draw a free body diagram, so here's mg, and here's n, and you can see the only component that is causing the acceleration is parallel components, which is mg sine theta, and this angle is theta. And you can see velocity is equal to initial minus a t. And you can see because the acceleration over here is constant, so the speed, which is the absolute value of velocity, is just basically a straight line. So the answer for this one is C, because velocity is always constant. And you can see because it is a straight line. So, and when you take a look at A, the velocity over here is, or the speed over here is negative, which is not possible. So it is not A. And for this case, it is not a straight line, so delete this one, and delete this one, and delete this one. And now, moving on to question 2, the answer for this one is E. And you might wonder, why is that the case? And why is a sharp turn over here? So basically, from energy conservation, we know that 1/2 mv squared plus mgh is always a constant. And when the ball is over here, you can see from this point to that point, if we assume h is very small or negligible, so basically 1/2 mv squared is a constant. So it is equal to mvx squared initial plus 1/2 m vy final squared plus m plus vx final squared. And you can see because there's a y component over here, and this equation is equal to each other. So you can see vx final is smaller than vxi. So basically, that's why you will have a term over here. And because the acceleration over here is mg or g sine theta, and if you separate the component to x and y, so you will have ax is equal to negative g sine theta times this angle, which is cosine theta, which is also constant. So it will be a straight line. So the answer is C. And moving on to question 3, if the system is at equilibrium, that means the total torque is equal to 0. And when you take a look at this point, so basically, if you take the system to be this rod, and here's another force going down, and we call it F double prime. So if you balance the force, you can see F times 2m is equal to F double prime times 1m. So now you have F double prime is equal to 2F. And from Newton's third law, we can see this force also F double prime. So F double prime times 0.5 m is equal to 2m times F prime. So F prime is equal to 0.5 divided by 2 F double prime. And F double prime is equal to 2F. So this term cancel each other out. So the answer is basically B. And for this question is kind of hard. Or if you want to solve this rigorously, you'll need to use calculus. And that's what are we going to do here. So first, we need to take a look at Coriolis force. So Coriolis force is equal to 2m omega cross v, where omega is the angular velocity. And in this case, we define the omega using the right-hand rule. So basically, if here's a disk and it is rotating around a pole, the direction of the pole is basically using the right-hand rule. If you bend your forefingers to the direction that is rotating, and your thumb direction is basically omega. So in this case, you can see the force is acting to that direction. So omega cross v prime is acting to that direction. Use your forefingers and bend it to that direction. And taking the opposite is just basically this direction. And in most cases, we assume that we basically ignore this term, which omega squared times r, the radius of Earth, and we call this centripetal acceleration. And if you take the frame as Earth, we often ignore this because it is too small compared to that term. And now, this omega is also very small. So we have the AC Coriolis acceleration is equal to negative 2 omega cross v prime, where v prime is a relative velocity in the frame of Earth. And now you can see this is basically d dt, yeah, and this is equal to 2 omega v prime. And because omega, this term, is very, very small, we often kind of ignore this, or we ignore this contribution to the velocity. So now, v as a function of t is equal to the initial velocity minus gt, and that is the velocity where we jump. And here's vt. And now you have dx dt is equal to 2 omega times v0 minus gt. And this term is also equal to dvx dt. And if you take the integral and move dt to that side, you take the integral, you will have bx as a function of time is equal to 2 omega v0 t plus omega gt squared. And if you take the integral again, and you know vx t is equal to dx dt, you will have x as a function of time is equal to 2 omega v0 t squared divided by 2 plus omega gt cubed divided by 3. And from the lowest point to the highest point, the time taken is basically equal to 2h divided by g, because we have the equation to be x or y is equal to y0 plus v0t minus 1 half gt squared. And this one is equal to t0. Wait, is that correct? Okay, okay, that's fine. So now, if we plug in, and we know that v0 or the initial velocity is equal to g times t. Because when you go from the lowest point to the highest point, the highest point has a v final to be 0. So basically v0 minus gt is equal to 0. You will have v0 is equal to gt. So this term is basically 2 omega gt cubed divided by 2 plus wgt cubed divided by 3. And you can see xt is proportional to t cubed. And we know that t is equal to that term. So now if you plug in the term, you can see xt is proportional to t 3 over 2. No, that is h02. And when we go from down, up, and up, down, you can see it is symmetrical. So basically, it is a factor of 2 if you take in consideration of from 0 to h, and here is h to 0. So you can see it is basically answer E when you jump as 2 times as height. You also can use dimension analysis to solve this problem. So basically, you consider that what is the dimension of x? This is basically rather. So how do I explain this? You just use dimension analysis, you can solve this problem. Moving on to question 5. This one is also very hard. And I don't think you can rigorously solve this without using multivariable calculus. So the official solution stated that like speed is equal to a1t1 and is also equal to a2t2. But that is kind of confusing, and I'm going to explain why that's the case. So first, we need to introduce you guys to finding the maximum with constraint, which is the gradient of f is equal to lambda times the gradient of g. So basically, what it's saying is that this is the function we want to find. And here is a constraint function. So in this case, the max or the minimum time is equal to, or the constraint in this case is that s is equal to s1 plus s2, where it is a constant. So basically, here's s1, which is accelerating with a1, and in s2 it is deaccelerating with a2, and s1 is equal to 1/2 a1 t1 squared, and s2 for symmetry we can see s2 is equal to 1/2 a2 t2 squared. And the constraint for this case is basically 1/2 a1 t1 squared plus 1/2 a2 t2 squared is equal to s. And g is basically equal to this term. Minus s. And the total time, or f, is equal to t1 plus t2. So basically, the gradient is equal to the partial derivative of alpha or partial T1 partial T2 times T1 or takes a T1 T2, and this is T1 T2. This is equal to lambda times the partial derivative of alpha T1 times this G alpha T2 G. So this is equal to lambda. The first term gives A1 T1, and the second term is A2 T2. And this term is basically 1, and this term is also equal to 1. So 1 is equal to lambda A1 T1, and 1 is equal to lambda A2 T2. You can see this term is just basically equal to each other, and you will have A1 T1 is equal to A2 T2. So that is how this term came to be. And now we can find the total time used using the average velocity over here. So basically T1 plus T2 times V by 2 is equal to S. Or no. The average velocity is V divided by 2, and you can see why. So here is a VT graph, and because the train is accelerating with constant acceleration, so the average velocity over here is basically V divided by 2. And that is the same case for when this deaccelerate with A2. So for this part, the average velocity is also V divided by 2, because you know that x is equal to the area under the curve. So for this part, the area over here is V times T1, and it is a triangle, so divided by 2. So average over here is V T1, 2 divided by T1, which is V divided by 2. So the same case for region 2. And now you will have T1 plus T2 times V divided by 2 is equal to S. And if you solve the equation, so A1 T1 is equal to A2 T2 is equal to V. If you plug in back to here, and you can get the T1 to be this. This question is really hard, to be honest. Okay, moving on to question 6. This question is also hard. I don't know why there are so many hard questions in 2021. So if you want to solve this question rigorously, you also need to use calculus. Oh my god. So a cylindrical bucket of negligible mass has a radius r, and you want to find the work done when lifting above the lake surface. So if it is a lake, we assume the water level is always a constant. So water level is constant. And now, when we lift this bucket from here to the surface here, you can see that the total force felt by the bucket is basically 0. Why? Because force balance each other out. So F buoyance is equal to rho water, GV, and Fg, which is water inside the bucket, is also equal to rho water GV, and it just basically cancel each other out. And now, when the bucket is above the surface totally, you can see the changing gravitational potential energy is just basically the work done. and that is the mass times the height, which is h divided by 2. So that is basically, I think that is c, right? Yeah. If you plug in m is equal to rho v, where v is equal to pi r squared times h. And if you want to solve this question rigorously, you will need to consider first, when the bucket is emerging a distance of x. And you can see the tension, or using the force balance. So tension plus the buoyant force is equal to Fg, which is equal to rho water Gv is equal to rho water G pi r squared times the total height. And F buoyant force over here is basically equal to H x. So buoyant force over here is equal to rho water G pi r squared times H minus x. And if you move that to that side, you can get T is equal to rho water G pi r squared times x. And the definition of work is T dx. So if you take the integral, you will have work done by tension is equal to rho water G pi r squared x squared divided by 2, where x is from 0 to h, which is also answer D. And now, question 7 is that a point mass slice with speed v on a frictionless horizontal surface of 2 parallel walls. So, and this was traveling with speed of 0.001 v. And for elastic collision, and here's the formula for elastic collision. So V1 final, V1 prime is equal to V1 final, is equal to M1 minus M2 times V1 initial, and we call V1 is equal to V1 initial, and plus 2 M2 V2 divided by M1 plus M2. And in this case, we're assuming that M2 is very large, or way greater than V1 prime. So basically this term just becomes M2 V1 plus 2 M2 V2 divided by M2. And wait. Yeah. So basically, this term is just now V1 plus 2 V2. And you can see V2 is equal to negative 0.001 V. So when the ball collides with the wall, it will gain a velocity of 2 times 0.001 V. And you can see the total time it collides with the wall is equal to this. And you can see the total velocity change is equal to the time it bounces with the wall times the velocity gain each time, which is equal to 0.0002 v, which is answer, which is basically D. And the other way you can solve this is to use adiabatic invariant. And this one is like not very hard or not very easy to explain. So basically, if you take the integral of this in one period, this term is equal to a constant. So what does that mean? So you need to define the px direction. So when it is going in the positive direction, px is positive, and when it's going in the negative direction, it is negative. So and we often assume in one period, the change in x is negligible. So now you'll have p times L minus negative p or plus negative p times negative L. That stuff is equal to a constant, where p is equal to nvx. And now you have vx times L is a constant. And when the wall is at length of 0.99 L, you can plug in, and you can see Vx final is equal to Vx initial divided by times L divided by 0.99 L, which is also gives answer D. You don't really need to know this concept, but it is kind of cool. And moving on to question 8. So basically, if you know, for this question, if you know the equation, then you're fine. So the equation is that when you have delta x to be constant, the total uncertainty of the average value is equal to the uncertainty divided by square root of n, where n is times in measures. So basically, if you plug in, you can see this term is equal to 0.1%, and this term is 1%. You can see square root of n is equal to 10, and square both sides, it will give the answer to be equal to 100. And for question 9, so NASA trains astronauts to experience weightless with an airplane which flies in a parabolic arc with constant acceleration g downward. And the plane can remain on trajectory at most 25 seconds due to large change in altitude required. If instead of stimulating weightlessness, NASA wants to fly the trajectory that will stimulate gravitational acceleration of Mars, assumes that maximum change in altitude is the same for both trajectories. So first, if you want to experience a gravitational acceleration of 3.7, and so first you need to know fictitious force. And if you don't know this concept, you need to search out. It's really important. This is very important. So basically, after the fictitious force, you can see that the plane should be accelerating at g minus its acceleration is equal to 3.7. So g prime is equal to 6.3. So the plane should be accelerating downward at 6.3 meter per second squared. So if you equate the equation, you can get the tau to be 31 seconds. Question 10 is to find the angular frequency of rotation of the disk. And it is on a frictionless horizontal table. And you will have a disk which has I of 1/2 mr squared. And you will have a stone over here. And the thing we know is that we need to note that the disk, it is not rotating around its center, okay? The center is not fixed. So basically, if you have this system, the center of mass is still, because there's no external force. So now you can take the center of mass to be a pivot. So you can see the center of mass is basically over here, which is r divided by 2. So basically now the disk is rotating around the center of mass. So I, or if you know the parallel axis theorem, which stated that I is equal to I center of mass, I plus md squared. So if you have a shape over here, and its center of mass over here, you first find the moment of inertia around the center of mass axis, and if the object is rotating around this point, which is at distance d from the center of mass, the moment of inertia is equal to I cm plus mg squared. And now you can see when the disk is rotating around this point, I is equal to 1/2 mr squared plus m r divided by 2 squared, which is equal to 1/2 plus 1/4, which is 3/4 r squared. And you can see for this point, the I is equal to m r divided by 2 squared, which is equal to m r squared divided by 4. So the total moment of inertia is equal to m r squared. And now you can see that initially the disk is spinning with angular frequency of omega 0. And you also need to know a theorem, which is the total angular momentum is equal to the angular momentum around its center of mass plus its center of mass angular momentum around the fixed point, we call it O. So basically, if you have a disk rotating at omega and its center of mass velocity is v0, and you want to find the L around a fixed point, and we call it A. So first, the angular momentum is equal to I omega, where I is the moment of inertia around its center of mass, and plus mvr, or mr cross v, and where m is total mass and r is the level arm from the center of mass to point A, and v is the velocity. And so now you can see as a total L around this point is equal to LCM plus L CO, where LCO is 0 because there is no initial velocity. It is equal to 1/2 I omega squared is equal to m r squared v final w final, and this is conservation of angular momentum. And you can see the answer is C. I don't know why does it make the test this so hard this year. I don't know why. What is the point? This question 11 is really easy. It's just basically D. There's not much to explain. And question 12 is also kind of easy. So, for wall V, will the platform never slip on the ground? So from energy conservation, you have 1/2 mv squared is equal to 1/2 ka squared, where a is amplitude, and you will have F is equal to Ka, and the net normal force is equal to M plus big M G. And you know that it is frictionless over here, and there's friction of mu is equal to 0.1 over here. So now you have the F maximum is equal to 0.1 times M plus big M G, and that is equal to Ka. And from this equation, you can know A is equal to a square root of mk time V. If you plug in, you'll have 0.1 M plus big M G is equal to K times M KV. So now you will have V maximum is equal to 0.1 times small m plus big M G divided by mk. Right? It's basically this, and you can find the answer to be C. And now question 13 is also easy. So you will need to know the total acceleration is equal to the tangential acceleration plus the acceleration in the normal. And we call this as AN, and this as A tau. So basically, let me see. You can see because the velocity is increasing, the tangential acceleration is in this direction, and AN is in that direction. So basically, if you sum up the vectors, you can see it is that the A total, it is basically this, right? I think so. And for 14, you will need to use dimension analysis. So first, it's stated that the drag force is a function of R, V, and U. And you assume the drag force is constant over here. And F is equal to M alpha M divided by S beta times kg divided by M times S, which is eta gamma. And this is in unit of kg times ms squared. And if you plug in the values, you can see A is equal to B is equal to C is equal to 1. So you need to assume the same amount of force. It is the same amount of force. So now you can see the speed is just basically doubled. So which gets answer C. And for 15, it is also easy. I don't know why always they put all the hard question first. So dumb. So first, you need to draw a free body diagram. So the parallel acceleration is equal to g sine theta. And you can see from, and here's ax, ay and ax. From geometry, you can see that, wait. So ax is basically equal to g sine theta times cosine theta. And which value minimize time needed to for the block. And you can see, because L is constant, you will have 1/2 ax t squared is equal to L. And you will have t is equal to 2L divided by ax. You'll have this to be 2L divided by g sine theta, cosine theta, and from the double angle identity, which is 2 sine 2 theta, it is equal to 2 sine theta times cosine theta. And you can get the term to be g sine 2 theta. And sine 2 theta is ranging from 0 or -1 to 1. And you can see the maximum is when sine 2 theta is equal to 1. And you will have 2 theta is equal to 90 degrees, and you will have the answer to be 45. And for question 16, you will also need to use calculus. Very funny, yeah, that is very funny. So first, you will need to write down the equation. V is equal to a constant kx minus plus v0, or k is equal to the slope, which is equal to negative v0 divided by L. You'll have v as a function of x is equal to v0 L times x plus v0. And now this is equal to dv dt. And from chain rule, we can see dv dt is equal to dv dx dt. Wait, let me see. Oh my god, what I'm doing. This is velocity, which is dx dt. So now you have dx divided by v0 L x plus v0 is equal to dt. And if you take the integral and let u is equal to v0 divided by L plus v0, you can see du is equal to negative v0 L dx. So dx is equal to negative L v0 du. And you will have L v0 times du divided by u is equal to t. And now you will have ln u0 is equal to v0 t divided by L and e. So u is equal to u0 e v0 t L, where u0 is an initial condition. So initially you will have x is equal to 0. So u0 is equal to v0. So v0 lx plus v0 is equal to v0 v0 t L, and you will have x v0 L is equal to 1 minus E v0 T L. And you will move to that side, L v0. Oh, wait. And you divide V. So basically, you'll now have as the equation to be x is equal to z. Oh my god. So x is equal to L times 1 minus E v0 T L. And if you take the derivative, you can have V is equal to negative L times E v0 T L. And you can see that the particle, it is not uniformly accelerated. But because A is equal to, oh my god, what is going on here? This one's V0. And this one's plus. So this term becomes a negative V0 squared divided by L E v0 T L. And from this term, we can have E v0 T L is equal to x divided by L. 1 minus x divided by L. So A is equal to V0 squared L times 1 minus XL, which is not constant, so not 2. It is not simple harmonic. It has E over here, so it is not. And you have that the particle instantaneously stops at x equal to L, so V. So now if you plug in x to this term, you'll have V is equal to V0 times 1 minus XL. And when x is equal to L, this term is just basically to 0, so 1 is correct. Or from the graph, you can see the velocity over here is just basically 0. And 17 is also easy. There's not much to explain, so the answer is C. And you can see that A is equal to omega squared R. So the answer is C. And 18, a factory smokestack continually produce smoke. The smoke always rises with a constant speed relative to the air around it. With a constant speed relative to the air. Suppose that the air was initially still, then abruptly started blowing to the right, then abruptly became still again for some time, which the following could show. Let me see. Yes, I think the answer is C, right? Always B, okay. Oh, I see why. So if you have a smoke over here, initially rising, and when the wind is blowing, all of this will move to that side. So at time t, it will just rise to here. And when it stops, it is right here. And for this part, you can see that the velocity of the wind is decreasing. So basically, I think this part, you guys just read this part. And for 19, so here's a cavity over here. and you want to find the magnitude of the gravitational field at point P. So how do you do this one? You just initially fill up the hole. So now, and you take the negative mass. What I mean by is that the first, has a mass of m, and it also has a mass, and the other ball has a mass of a negative m. So when you combine them together, it will just act as an empty hole. So first, you will need to fill up the hole. Oh my God. With positive m. So it's the same as producing a gravitational force as the center. So it is g big M small m divided by r squared. And now you need to consider the force of the negative mass. The negative mass is just basically repelling the point P. So if you calculate the force in the x direction and the force in the y direction and take fx squared plus fy squared, you can get the answer to be this, which is C. This question is really hard to calculate. Question 20 is kind of stupid. So you'll need to note that the same side of the moon always faces the sun. So it is basically that the moon is rotating, and it is the center mass is also rotating around the Earth. So the velocity is equal to this. I think that's stupid. I don't really like this question. And moving on to question 21. I think the answer is probably A. Yeah. So first, you will need to consider when the ball will slip or not rolling without slipping. So first, you have a constraint over here, which is rolling without slipping. And the extreme case is that F is equal to mu s mg, or mu sn. And from a free body diagram, we can see that n is equal to mg cosine theta. So, and you will have ma is equal to mg sine theta, minus the friction experienced. So this is mu s mg cosine theta. And the constraint over here is that A is equal to the angular acceleration times r. This is the equation you need to remember for constraint. And also V is equal to omega r. Those are the two constraints for rolling without slipping. And in the stellar mass frame, you'll have Fr is equal to I times alpha. So now you'll have Fr is equal to I times AR divided by R. So F is equal to I A R squared. And plugging into this equation, you will have MA is equal to mg sine theta minus mu s. What I'm doing here? Actually, no. You can get the acceleration from this equation. So m is equal to g sine theta minus mu s g cosine theta. And this, and from the constraint, you can see alpha is equal to a divided by r. So you will have fr is equal to I divided by it's kind of like this. So you'll have f is equal to I times a r squared, and you will have f is equal to mu as mg cosine theta, and you plug into that equation, you will have mu as mg cosine theta is equal to I a r squared, which is equal to, and here's a solid sphere, so it is 2/5 times g sine theta minus mu as g cosine theta. And you can get mu as cosine theta is equal to 2/5 sine theta minus mu as times 2/5 cosine theta. And move that term to that side, you will have 7/5 cosine theta is equal to 2/5 sine theta. And move cosine to that side and this to that side, you will have tangent theta is equal to 7 divided by 2 times mu. So theta is about 35 degrees. And now moving on to question 22. So a ship ran into a hunk of ice floating in the sea. Icebreakers are ship designed so that when this happens, the ice is pushed down beneath the ship. If the coefficient of static friction between the ice and the ship is mu s, what condition applies to the angle theta as shown in figure so that icebreaker functions as intended? I also think this problem is kind of stupid. So first, you'll have a normal force acting in this direction. And the ice also experiences a friction force in that direction. And the maximum of friction is equal to mu s n. And now, if the ice is pushing down, basically, you'll have a y component of the force that is going down. So basically, if you take the sum of the forces, here's theta, and here's theta. So basically, you need to have F or n times cosine theta minus F times sine theta is greater than 0, which gives the condition to be n cosine theta minus mu as n sine theta is greater than 0. And now you will have mu as tangent theta is greater than 1. Or wait, is that true? It's n cosine theta is greater than mu s n sine theta. And now you will have a cotangent is greater than mu s, which is answer A. And 23, which is simple harmonic motion. So for this region, it's going from here to here, and release from the rest position of A, so this point is A. And you can see for simple harmonic motion, x is equal to A cosine Wt plus phi. And in this case, phi is equal to 0, because it is at the starting position. And where omega is equal to km. And now if you take the derivative, you can see v is equal to Wa sine omega t. And at this position, you can see the velocity is at maximum. So this is equal to Wa. So it wants to find the period. It is going from here to here to here, and then here to here to here. So first, it is basically finding 2 times the period of here to here to here. And for this part, the time it takes is basically equal to, and if you draw a circle, it's going from this to this direction. So it is pi 2 divided by omega. That's equal to pi divided by 2 times mk. And here's double of this, so times 2. And for this part, the time it takes is 2d. So the length of here is 2d. Divided by the velocity, which is equal to Wa. So this part is 2d a times mk. So the time it takes for this part is equal to pi mk plus 2d a mk. Wait, the amplitude for this part is a minus d. My mistake. So basically, you need to time this by factor 2, and where this part is a minus d. And the answer is, I think, it's C, right? Yeah, I think C. Yeah. Okay, question 24. We're almost done. And you will have a planet over here. And it is in a circular orbit. Initially. And the star, it is at R and B and opposite of each other initially. And in order to meet the second satellite in time t divided by 2, the first satellite should decrease its speed 2. So basically, the shape of the second satellite is basically ellipse. So the period for the ellipse is equal to t divided by 2. And you know that g divided by g big and small and divided by 2a is equal to the total energy. Where a is this part. I kind of forgot what it's called of the ellipse. And you will also need to know that A3 divided by T2 is equal to a constant. And this is equal to r3 divided by t squared. So this is equal to a3 divided by t ellipse. So a is equal to r times t ellipse divided by t squared. And here's 2/3. Let me check. Okay, this is correct. And here's a new a. And from conservation of energy, this term is equal to negative g big M small m divided by r plus 1/2 mv squared final. And if you plug in back, you can see now this term is equal to g big M small m divided by 2 times r times 1/2 2/3 plus g big M small m r is equal to 1/2 mv final squared. And mv initial squared divided by r is equal to g big M small m r squared. So you will have mv I divided by 2 is equal to g big M divided by 2r. So the ratio is basically this term, g big M small m 2r divided by this term. And you'll need to take the square root of this term. And you can get the answer to be this. Yeah, this question is hard. Okay, moving on to question 25. I think this question is fairly easy. So basically, if you observe and set an angle to be theta, and here's velocity of v. So when the object reaches a planet, like the most extreme case is when the object reaches the planet with a velocity tangent to the surface. And we assume that h is much larger than r, so now you will have, using the conservation of energy, you'll have g big M small m divided by r plus 1/2 mv squared is equal to g big M small m. Oh wait, this is h divided by r plus 1/2 mv final squared. And from angular moment, a conservation of angular momentum, you'll have v sine theta times h is equal to v final r. You'll have v final is equal to v initial sine theta divided by r. Yeah, I think that's it. And if you plug in the term, and because this term is way larger than this term, you just ignore this term. You can have g big M small m r is equal to 1/2 m v0 squared times sine theta h r squared minus 1 And from the condition is that these pellets are launched with the same speed, so that the pellet launched directly away from the orb, just barely escape it. So that means the total energy of the orb is equal to 0, which means that negative g began small m r h plus 1 half mv0 squared is equal to 0. We have 1 half mv0 squared to be the g began small m divided by h. So now you can see this is equal to g began small m divided by h. You can move the h to the side. You can have h divided by r. This equal to sine theta h r, and these now you have sine theta is approximate to RH, right? And this angle is really small. So basically a theta is approximate to R divided by H. And you want to find the portion where it like land on the planet. So basically this part. So theta over here and theta over here. So the total fraction is 2 theta by 2 pi, which is 1 divided by pi times theta, where theta is equal to this, which gives answer to be E. Okay, we're done.